welcome back again. Anyway, previously we took a look at the four-step optimization procedure and used it to figure out a couple of numbers that had a product of 185 with a minimum possible sum. So that's good, but again, it feels like something that you would only be doing inside a math class. It's not something you'd have to do once you're done with my course. So I wanted to take a look at the next example that was listed. Before, you didn't really have any guidance. We just kind of gave you the constraints and said, here's what we need you to do. Now we're going to apply that four-step procedure in order to see what's going on and come up with the desired quantities. As a heads up, remember I posted that four-step procedure as a handout in Moodle. I'm taking for granted that you have it available at the moment, be it a printout or the PDF just sitting alongside the video, whatever floats your boat. So taking a look at this, we got a picture of what our setup looks like. So we've got a farmer who wants us to do this with a pasture for animals. Come up with whatever type of situation warrants a pasture that looks like this. I'm not an agriculture expert. I'm not going to claim to know why you'd want to do this. Anyway, so we've got two horizontally running pieces of fence. That X covers the entire length, by the way. That's not just like a midpoint or something. We have three vertically running pieces of fence that we've labeled Y here. We gave you a picture in this instance. FYI, very often I find that students find it beneficial on problems like this to draw a picture even if one's not provided. That often gives you some guidance as to how you might want to construct things. Okay, the setup is our farmer, for some reason or another, has 4,800 feet worth of fence, 4,800 feet. And he wants to enclose as much space as possible with that amount of fencing. So that's our objective at this point. As I mentioned last time, our four-step procedure spells things out so that we want to identify what we call an objective function and find a formula for it. It's, again, kind of given away in this instance that we want to maximize the area of this pasture. So step one, we want to find a maximum for our area. And hopefully you remember that if we want to find the area of this thing, since it's a rectangle, that's just length times width, or given our variables, x times y. Okay, awesome. That's what we're after. The catch is, we've got one extra constraint to work with, which is good because we have one too many variables here and we want to knock that back down to where we have just one. So the other constraint we have to work with is the 4,800 feet worth of fencing that our farmer has available for us to use. Now, since this thing is a rectangle, and we can kind of measure out our pieces, as I've already spelled out, we've got two horizontally running guys that should be length x. So we have 2x. We've got 1, 2, 3 vertically running pieces. So we have 4,800x. Pardon me. We have 4,800 equals 2x plus 3y. So we can use this equation to get one of the two variables by itself. Like last time, I'm going to isolate y, so that's up to you if you wanted to go the other way, but picture, you've done your job. So to get y by itself, we subtract over the 2x, then we divide by 3. I'm going to clean it up a little in the interest of saving board space. So you'd have 1,600 minus 2/3 x once you get y by itself here. Again, if you'd left it as the whole thing divided by 3, that's fine, but I think it's a little nicer for what we're going to do next if we go ahead and clean it up. So now, so that's what our objective function is going to look like only in terms of x. X times this guy, 1,600 minus 2/3 x. Usual algebra maneuver, I'm going to distribute the x because it's going to make the calculus easier that we've already seen that's going to come in the future. So our objective function looks like 1,600x minus 2/3 x squared. So it's a quadratic polynomial, one of our favorite things that, if we need to take a derivative to work with. So step one, we had our objective function. Step two, we've got it down to where we have just a single variable in it. Now we look for critical numbers like we did in the previous example by taking a derivative and looking to see where it's equal to 0. So again, running through our derivative techniques from previously in the course, the derivative of 1600x is just 1600. Power rule says we pull the 2 down out front of that guy right there, so we'll have minus 4/3 x. 2 minus 1 is our new exponent. 2 minus 1 is 1. So there's our objective function's derivative. This time around, we don't have to worry about this thing being undefined anywhere because it's a linear function and they're about as well behaved as they can get. So we set that guy equal to 0, and now we get x by itself. So however you go about doing this algebraically, we get the 1600 on one side, divide by 4/3, which I'm going to write that as multiplying by 3/4 just to save myself board space again. So 1600 times 3/4, if you work that out, that gives us a single candidate point, 1,200 feet. So step 3 done. Now, like I said before, we want to make sure that we are in fact maximizing this farmer's real estate. We don't want to give him the smallest pasture possible. That would be, he'd not be happy. So next time around, I'll leave my derivative formula there so I can point at it in the future. But so a prime of x up top, like I said, I've just had a thing about labeling these diagrams. Like before, 0 makes sense. It's just a hard cutoff. You're not really going to tell the farmer to use a negative length of fence. So, I'm going to cut things off at 0. We've got the tick mark at our candidate point 1200, and we want to see what the sign of our derivative does in each of those 2 strips of our number line. So, good number between 0 and 1200. If you can pick one, generally do it. Coming back down here, plugging 1 into this thing, 1600 minus 4/3, that is definitely a positive number. So we got a plus sign right there. So that's good. Our area was climbing up until we got to 1200. That's a good sign. So now let's see what happens once we go past it. Again, we're at liberty to pick any number we like bigger than 1200. Again, I'm going to go with 1 million just because it's a nice round number and it feels fun to say. Anyway, 1600 minus 4/3 times 1 million. Yeah, hopefully you don't need to put that into a calculator to determine, yes, that is in fact going to be negative. The million thing in the back is bigger than the 1600 that's in front of it. So this does indicate what we want for a maximum. We were climbing, we flattened out at that critical number, and now our area is dropping again afterwards. So yes, we do in fact have a maximum here. So we need to tell the farmer what he's wanting to do with this. We don't just say x equals 1200 and then try to collect our paycheck. We actually want to give him the dimensions, and he also asked for what area he's going to be able to enclose with his fencing. So x is 1200 feet. He also needs to know that vertical measurement, the y. We can get that from what we did previously. So we take 1600 minus 2/3 x, plug in our target x value, 1200. 1600 minus 2/3 of 1200. If I'm doing my arithmetic right, and I'm pretty sure I am, we've got 800 feet running in that vertical direction. So you can double check and make sure that these numbers, when you feed them back in, do in fact use up all 4,800 feet worth of fencing. So to calculate the area, we can take these 2 values, multiply them together. And we should have a maximum area in this instance of 960,000 feet squared. Again, not an agriculture expert. I have no idea if this is feasible or not for whatever types of livestock this farmer has. I don't know. I'm just having to go with what I'm given here. So that's where we stand using this 4-step procedure rather than just kind of throwing numbers at this and seeing what ends up sticking and doing what we want. So that's that. I'm a little short on time to try to do another example, so I think I'm going to pause it right here, and then we'll pick up another example momentarily.